Welcome back to che531. In this video I'll be talking about successive substitution method to find the roots of a function. In the last lectures we talked about three methods, including bisection, Newton's method, and secant method. So in Newton's method, which is the best one in terms of convergence, we do need the derivative of a function. However, in secant method, we don't really need the derivative of a function. We can approximate the derivative by some sort of differencing. In successive substitution, we don't need derivative of the function either. So this is pretty much like secant method, but in secant method, we approximate the derivative. In successive substitution, we don't really deal with the derivative at all. So imagine we have a function f of x, and we want to find the root of the function. So imagine the function looks like this, as just for example, x to the fourth power minus exponential of x plus 1 equals 0. And you want to find the root of this using successive substitution. So to follow this this method, we need to split the function and write it in the form of x equals some other function, call it g of x. Okay, for example, in this case, I can have x to the fourth power on the left side and move exponential and 1 to the right side, and then take the fourth root of both sides. Then I can have x equal 1 minus exponential of x raised to the 1/4 power. Okay, so this is one way to do it. And by the way, there's a typo here. This should be actually exponential of x minus 1 raised to the 1/4 power. Okay, we can have we can have x equal g of x in different ways. It's not a unique way of doing this. So this is one form of it. Another form is, let's say I keep exponential on the left side and move x to the fourth power and 1 to the other side or to the right side, and I get the quotient like that. And then I get the log of both sides, and I get x equal log of 1 plus x, well, actually to the fourth power. This should be to the fourth power. So you see that now I have x equal g of x, so my g of x is log, as opposed to this g of x, which was exponential minus 1 raised to the fourth power. So it's not a unique way of doing this. Depending on how we split it, the convergence of the method will be different. Okay, so none of them are wrong, or none of them is wrong, and none of them actually is correct. We can't say anything unless we check the conditions we're going to see in a minute. And we basically program it and use an initial guess and see, which one converges faster, which one converges more slowly. Okay, so the condition for successive substitution is that the derivative of the g of x should be less than 1 in the area or in the range that we use initial guess and we want to find the root. If this condition is not met, then the method is going to diverge. So here is pictorially how successive substitution works. After we convert a problem into x equal g of x, we can basically split this equation, this x equal g of x, into two equations. One is y equal to x, and the other one is y equal to g of x. Okay, so apparently in this picture, or in this plot, we have two functions, and we want to find the intersection of the two. Y equal x is one function, y equal g of x is another one, and the intersection is where x equal g of x. So we have converted the problem of f of x equal to 0 to x equal g of x by intersecting two lines. Okay, now the way that successive substitution works is the following. We start with a guess, x naught. So here's x naught. I just locate that on the y equal g of x. Okay, and then look left or right and see where the line y equal x is located. Now in this case is on the left side, so I'm going to move horizontally until I hit y equal x. Once I hit y equal x, I actually go down until I find the same point on the curve. So that's going to be the next point, or x1. Okay. From this point on, I repeat the cycle. That means I go left again until I hit y equal x. Then I go down to sit on the curve for x2. Okay. Again, from this point on, we go left and then down to find x3. Again, left, down, left, down, left, down, until we get close enough to x to the fourth power, or sorry, to the root of f of x equals 0, or the intersection of x and g of x. Okay, so this pictorially shows that the method actually is converging. However, I can show you an example that the method actually does not converge. So here's an example. I have the function which looks like this curved line, and here's my y equal x, and let's say I'm interested in the first intersection right here. I start with initial guess for this point, like x naught, which is located right here on the curve. And this time I don't go left because y equal x is not on the left, y equal x is on the right. So I have to go right until I hit y equal x, and then go up to find the next point on the curve. So initially I started from this point, and now for the second cycle, I'm sitting right here. If you do one more step, then it's going to go to the right and up. You're going to find the next point, which is down, well, very, very up, maybe somewhere here. Now, if you look back, you see that we started from here. Next cycle, we got this one. Next cycle, we got this one. So it looks like we're going further away from the intersection point. Okay? Yes, so that means the method does not converge in this case. And the reason is because when we use initial guess of x naught, at this point, the slope is bigger than 1. So the slope 1 is the slope of this line, y equal x, right? Anything steeper than that will have slope bigger than 1, okay? So this one has a slope bigger than 1, and that's why it's not converging. I've heard from students most of the time that they say, oh yeah, actually it is not converging because this y equal x is sitting on the right side. And this one is actually converging because the y equal x is sitting on the left side. Indeed, that is not the reason. You can easily show that even if the curve is sitting, or the y equal x is sitting on the right side, you can have convergence. Like in this case, we've got divergence. But let's say somewhere down here, if you continue this curve, you see around this area, the slope on the curve is smaller than y equal x. And you can basically start from somewhere here, initial guess, and you see that actually you're going to converge even though we go to the right to make steps, even right here. So if I continue this and start from a point here, the next cycle actually have to go right and then up. So being on the right or left is not the convergence criterion. The convergence criterion is the slope of the tangent at the point that we use as the guess. Okay, so so we talked about how we can convert f of x to x equal g of x, and we said the multiple options, one could be better than the other, depending on the range of the derivative and initial guess, and these parameters. So again, back to the example we talked about initially. I can have g of x equal to x to exponential of x minus 1 to the 1/4 power, and this is if I move these two to the right side and then take the fourth root, or I can move x to the fourth and 1 to the right side and then take the log. Okay, so if you script these two functions, you would see that the first one, convergence to the first root, looks like this problem actually has 3 roots. This function leads to the middle root, and this function leads to the first and the last root. Okay, so depending on what function we use, what initial guess we use, we can have either 1, 2, or sometimes actually none of the roots. Okay, so here's another example, x tan x minus 1. You want to basically convert it into x equals g of x. Then one way is you divide through by tangent, okay, and move 1 to the right side, then divide by tangent. We get something like this, x equals 1 over tan of x. Okay, and so if you go ahead and check the convergence condition, which is derivative of g of x, you get a derivative of it, and you see that it's actually bigger than 1. Okay, so that means this one actually does not converge. This g of x does not converge. Another way to find g of x is we move 1 to the right side, then divide through by x. Okay, so then we get tan x equals 1 over x. Then we get arc tan, or tan inverse. Then we get a function like this, which is tan inverse of 1 over x. And if you calculate the derivative with respect to x, you see that the derivative is actually less than 1, which means this is gonna converge, okay, because it satisfies the condition. All right. So at this point, I'm gonna switch to MATLAB script, so we can see actually the code. So here is the code for successive substitution. I clear the screen, I clear all the variables, I close all the figures. By the way, I have actually 2 functions. One is the main and the other one is the function. So I'm talking about the main at this point. Let's say the first example we're going to look at is z to the 4th power minus exponential of z plus 1. In this part, actually, I'm plotting it to see where my root is going to locate. So I'm going to put a breakpoint here and run it up to there, just to show you, how the function looks like. So there's one root here, one here, and then one here. So in this area, actually hits the x-axis twice. One root is sitting also here. So total, there are 3 roots. Okay, so just by looking at the plot. Okay, now the first way is I'm going to split this into g of x by moving exponential of 1 to the right side and take the 4th root of both sides. Okay, and so if you do that, then you would see that this is going to be our g of x. This is my f of x. Okay, and I provide some initial guess, a threshold for convergence check, and then maximum number of iterations. Okay, I feed all of them into my function definition. Okay, and then later on down in the code, I define what this is. So this is the end of the main in the function script. Okay, now I'm going to define what f is, what g is, and other variables. So f is going to be the first argument, which is x tan x minus 1. G is the second argument, 1 over tan x, and x is the initial guess. In this case, is pi over 8. Epsilon is 10 to the minus 4, which is the threshold, and maximum number of iterations is 100. Okay, all right. So in this function, I first create the headers for my table. I'm going to make a table of x and g of x, number of iterations, f of x, and the error at every step. Okay. So in the next video, I'm going to show you details of how the script is going to look like, and basically we go ahead and execute the code and see the result. So stay tuned, and thanks for watching.